As people are coming in, if you would like to participate in our Menti poll, this is going to be accessed by going to menti.com and typing in the 8-digit code, or you can use your phone to scan the QR code on the screen and answer a few icebreaker questions as we're waiting to get started.
I haven't been asked my favorite color in a long time. This is fun.
Means you haven't watched The Holy Grail recently. All right, good. We just crossed over 100 participants, so welcome everybody. We're going to start in just a minute or so. And if you're just joining now, you can participate in this icebreaker on menti.com and typing in the code, the 8-digit code there in the top right of the slide, or you can scan the QR code, or I can't see the chat because I'm sharing, but I think that we have the link in the, yeah, I see some head nodding. So you can access, oh, here we go. I can move the chat over here. Okay. I see a lot of people using the chat and putting in where you're joining us from in the chat. Thank you for doing that. I would also appreciate it if you can also do that in Menti, just because that means I only have to go to one place to collect everyone's location when I make a map at the end. But it's great to get the chat started. Okay, so welcome everybody to today's webinar. Today we're going to be talking about the geology of pigments. Just as a reminder, this webinar is going to be recorded and is going to be placed on the AAPG Women's Network YouTube channel. So just an FYI that everything that you're going to be seeing today is going to be captured and shared for posterity. This is the next installment in our popular Geology of series. These webinars began during the COVID pandemic as a way to foster professional networking amongst our membership and also the general public in combination with education on the importance of the role that geology and geoscience plays in our everyday lives. We've done some very well-received events in the past, including the geology of wine, beer, coffee, whiskey, and we were just commenting this is one of our first inedible, non-consumable ones that we've done. So we're excited to have you all learn today about the relationship between geology and pigments and paints, and that's going to be accomplished through a combination of interactive painting and some technical presentations. If you have any questions during the presentation for our expert panelists, please put them in the Q&A section of Zoom. And we're going to have a little Q&A section at the end where the nice thing about using the Q&A versus just putting them in the chat is that other people can like upvote them and we can, high grade the questions if we have a limited amount of time. Feel free to use the chat though for any socializing. And then at the end of our scheduled content, we're going to open up the Zoom session. Right now we have it as a webinar style, so you're not able to unmute or share your video. But at the end, when we're done with our technical component, we are going to open it up for everyone to have some socializing time. Maybe if we don't get to all the questions, we can see if our panelists can stick around a little bit for some of those. I'm only one of, my name is Stefano Mazzoni. I should have said at the beginning, I apologize. I'm only one of several very awesome volunteers that put this series together, and I'm going to pass it over to our next volunteer, Kat Gould.
Hi, I'm Kat. I have been volunteering with this group for a few years. I'm a geologist by training. I'm up in Canada, and yeah, I'm really excited about the event today, and I hope everybody has a great time. Okay, I'll pass to Dan next.
Cat. Cat.
Yes.
I heard you say you're going to pass it to me.
Yeah, I think we're doing introductions for
Just our own introductions.
yeah, our own introductions. Yeah, I'll pass it to you, Dan.
So I saw the panelists on here, and I thought you were going to read the instructions.
No worries, no worries.
All the panelists. Yeah, I'm Dan Kelleher. I'm a hydrogeologist with Midwest Geosciences Group. I'm just a volunteer here, a simple soldier, and you know what? It's a great experience for everybody online. Feel free to call out and chat with any of us as we move along. Welcome to everybody.
Okay, well, I guess I'll pop in. Hi, this is Carla Tucker. I'm a geologist in Huntington Beach, California, recently retired, so I can fill all my days with this fun volunteering stuff now. So welcome, everybody. I'll be monitoring the chat and looking forward to this great webinar.
Chris, if you're able to unmute, go for it. If not, Kat, do you want to introduce our panelists?
I'm Chris. I help with the geology of wine seminars. I have a winery and I live in East Texas, and I'm a geologist, and I currently do exploration for gas in the Caribbean for BP. And Kat, I hand it to you for intros for panelists.
Yeah. Yeah, thanks a lot, Chris. Yeah, so I have the great pleasure of introducing this really diverse and fantastic group of panelists that we've assembled, and they are going to bring something unique. Each bring something unique to the presentations and the discussion today. So I'm going to give you the highlights for each of these folks and introduce them before we then go on with the webinar. It's really hard because they're all very interesting, so I'll try to keep it short and sweet. But we're going to start off with Cristina. So Cristina Mazzoni is, and sorry if I mispronounced that, but she is a Mitre Green and Gold Professor of Romance Languages at the School of World Languages and Cultures at the University of Vermont. So she teaches Italian studies and European fairy tales, which sounds very interesting, and has been painting for a very long time. And she's working with artisanal watercolors for the past 5 years. She uses synthetic pigments in her painting. And when we brought her into the group and she met Chuck and Bob, she said, "Oh gosh, I use your guys' paints already." So she's excited to be here, but we're excited to see what she can bring for showing us the painting, the interactive piece. And then next up, we have Dr. Sister Mary Virginia Orna. So she's a professor emerita at the University of, or the Chemistry College of New Rochelle. So aside from being part of the Order of St. Ursula, she is also a former director of educational services at the Chemical Heritage Foundation. And she's also worked with a number of other important chemical journals and has a PhD in analytical chemistry. So she's lectured and published a wide number of articles and books on color chemistry and archaeological chemistry. And she's written a really exciting book that I know some of us have already picked up called The Lost Elements, the periodic table of shadow sides. So she's written that book and also a book called March of the Pigments. So you should check out her books if you're looking for more information on these topics today. She's received numerous awards, teaching, innovation, volunteering. She has a number of very interactive and intellectual hobbies. So we're really excited to have Dr. Sister Mary here with us today. And then next we have Charles Chuck Hoover, who is I love this, fourth generation color man. So Chuck is a geologist by training, and he has been working for many years with his family's pigment factory. So he's been a prospector, he's been a miner, but he's also worked in his family business. And he's been working now with Hoover Colors as a system analyst, and he's now the president and CEO of this company. So he is going to bring us a background in both geology, but also working basically inside of the paint industries. So we're really excited to hear him talk about colors and how rocks and minerals impact the pigments that we use day to day. And then last but not least, We have Bob Hedin. Bob is the president and owner of Iron Oxide Recovery. So Bob works specifically in mine drainage remediation. He's worked in that career for a number of years. He has a consulting firm where he's designed many different types of passive treatment systems to remediate mine waters from contaminated sites. So he's pulling out and working with contaminated sites of iron and aluminum and manganese. And he takes out that clean iron oxide, and he also works with Chuck on the Hoover Color Company to develop these EnviroOxide pigments from this recovery. So he does a lot of really exciting work. He's pulled over 6,000 tons of iron oxide recovered from mine waters and turned that into environmentally recycled or safe pigments. So he's going to talk to us specifically about iron contaminated mine waters and common ways that you can use pigment, iron and pigment quality kind of iron oxide inside of paint pigments. So really excited to hear those. So I hope that was probably longer than intended, but we're really excited about this group of panelists. Yeah, I'll wrap it up from there, but you're going to hear more from each one of them individually. Okay, so I'll pass it back. Thanks.
Great, thank you, Kat. Next, we're going to have our first of our interactive painting sessions. So I'm going to stop sharing my slides so that I can spotlight Cristina's painting. There we go.
Yeah. Our first question was, are these pigments edible that people received in the mail?
I'm not going to answer that. Chuck or...
Can Cristina hear me?
I would say don't eat them.
Yeah, there are certain grades of these pigments that are used as food colorants, but they are controlled for, especially in the inorganic side for, their heavy metal levels. And so the same color that you'd use for a house paint, you would not necessarily use for a food colorant.
Great, thank you. All right, Cristina, take it away.
Can you hear me? Can you hear me? Yes.
Yes.
So these are some of the colors I've made in the past, and some of these are definitely toxic. I would say do not eat pigments. There's a lot of good food in the world. Pigments are not one of them. The first question that you might ask is, what are watercolor paints? I'm not going to talk much, but I have to tell you first. They come in a variety of shapes and sizes. These are the ones I made. These are commercial. And they all start with a pigment, and I'll show you the beautiful pigments that Bob sent. Well, we actually only use these two. So you start with pigments, and then you add a binder. Now, depending on which binder you use, you end up with different paint. So if you have oil paint, you use linseed oil, you use egg yolk for tempera. For watercolor, the key binder is gum arabic. And these are some gum arabic, beautiful jewel-like sap. It's hardened sap of trees. And then different makers add different additives to make the binder more effective. I use the very basic, which would be honey, vegetable glycerin, and this is just my own signature of oil of bergamot. Essential oils are often used as antibacterials and fungicides, plus they make the paint smell good. So my binder actually is food grade, but most pigments aren't. Then what you do is you mix the binder with your paint, with your pigments, and oops, I want to show you, this is my collection of many of the earth. These are all made with earth and mineral pigments. You mix the binder with the pigments, and then you go like this for a long time. This is called a muller, and it's glass, and it's used to really mix the color with the binder. So it's very nice. Now, if you got Pigments in the mail, you got either these two or these two. We ran out of the Environox pigment, so then I started using Italian Yellow Earth and USA Burnt Sienna. They're both very similar sets, and it's what I'll use. If you have your own, that works. The other thing that you will definitely need, these are fancier. The other thing that you will definitely need is watercolor paper. Now, most paper that's not watercolor paper will not work because it doesn't have the right sizing and the paint will go through. However, sometimes there's paper that you don't think will work and will. So if you don't have watercolor paper, try with what you have and hopefully you will get a bug for watercolor painting. Now, as you can see, I'm putting little drops of water to activate the paint. And the first thing that I would recommend you do is swatching. Some people, that's all they do is swatch paint because it is such a wonderful thing to do, just to see the paint and how it blends and mixes, and you see how it stays in the little crevices of the paper. It's just a very lovely, soothing, calming pastime. Now up there, I swatched the Environox paint pigments from Bob, and below are these earth pigments, one from Italy and one from the USA. And then you mix, and mixing is fun. Mixing these two is not that exciting because they're similar to each other. But look what happens if I happen to have some genuine lapis lazuli. If you add lapis lazuli to brown, you'll get a nice gray. So try any blue if you have a blue, even a blue pen. But this is what ground high-grade lapis lazuli looks like, and it's gorgeous. The next thing I encourage you to do is maybe draw with a pencil or just leave a lot of white around so that the paper won't buckle. You have smaller pieces of paper, but this is better for demonstration purposes. And watercolor painting is made up of two basic activities, washes and brushwork. And here I'm doing a wash of just one of the colors. You can give it a shape or not. And then I can add the darker color, and you could just enjoy, play with just the water and let the two colors blend with just the gentlest touch. And then you can put this away and we'll play with this wash later. You can also do this and see how the water doesn't really go, the paint doesn't go where there is no water. Another fun thing to do is brushwork. So that was a wash, and we'll do brushwork now. And this is a Japanese image that is just a wonderful thing. It's called enso, which means circle. And you hold your brush like this, and you just go around in a circle. And I've read that there are artists that all their life, this is what they do, only ensos. It captures a moment in time. And supposedly you should only have one, at most two. But I like my ensos chubby. So since this brush is small, and as long as your paint is wet, you will have a nice blend of the colors. So I hope there are many ensos in your life in the future. Something else that you can do with, I'm just doing a whole bunch of things, and then hopefully will inspire you to do more when you have time. It's springtime in Vermont, and two of the first flowers we see are crocuses and tulips. And with brushwork, I don't know if you can see what I'm doing. I'm not really drawing a leaf. I am just pressing with more or less pressure on the paper. And that creates a leaf. So light pressure, you have a thin line. Heavier pressure, you have a thicker line. So you can also just do a bunch of leaves here. And then if you want to do a tulip, say, tulips are easy because I don't have a lot of. And you're welcome to draw first if you like. Sometimes I draw first, but it is pleasant to just kind of paint. And again, just by using your brush very lightly, you end up with a thinner line. I mean, these are not ideal colors for a tulip, but so what? And then you can have another leaf. Now, let's make a pear. These are the perfect color for that kind of pear, the name of which I always forget. Forget about doing like an outline and then color in. Just use your brush. And use your brush to bring into the world the first and only pear of now. And you can use a real pear for pears have always attracted artists. I don't know if it's because they're shaped vaguely like women's bodies, but they're very popular. And then if you just dump some water in your painting, it'll create some nice effects. That's why it's called watercolor. It likes water. Now I'll show you another trick. If you have a pen that's not water soluble and you touch it onto this, look, you get a little, what do you call it? The blossom end. And then you can do a little stem here. And then if you want, you could drag some of this and it will give you a shadow of sorts. I really love doing pears. And if you pull out some of it with a brush that doesn't have any paint in it and you do this, you can lift some of the color and then you have like a little shiny, lighter center. So what else? Oh, this is in honor of my children and my siblings who are all cat ladies. I'm allergic. But this is also a fun way to use your brush to create a creature. And you have a cat with the ears. It's a cat from behind, so you don't have to deal. And then the back. And then the haunches. And then, of course, the tail. And here too, you can give it some dimension by using another color, especially around the edges. And then another little trick, if you take the back of your brush, it'll give you some very thin whiskers. You know, you keep shaping it as you desire. Here too. You can add water if you want to have some more interesting texture once it dries. The ice cream truck is coming by here.
Christina,
Yeah,
code word pigments.
yes.
Remember that?
So we can stop here, and it's a good time because now these 5 little paintings we've done are drying. So you let them dry, leave them alone, enjoy the show, and we'll come back later for a second layer.
Great, thank you, Christina. I'm going to pass it over to Mary Virginia, and you should have control of your slides. But we need you to unmute, sorry.
Thank you very much.
There we go.
I'd
Now we
like
can
to
hear
move
you.
on to something quite different, and that is to talk about in 14.7 minutes, 14.7 billion years of the evolution of mineral pigments. And to do that, we have to talk about, first of all, the analysis of pigments, which you have all already realized is a colorant that needs a binder, such as water, oil, or whatever. But that once you analyze, you then begin to learn a lot more about sociological contexts. You learn about cultures that maybe existed long before other modes of cultural transmission. And you also really then enable yourself to look on a disappeared world. But one other thing that we have to say about the analysis of pigments as such is that also they evolved along with the ecosystem and with living beings. And that is what I would love to talk about today. So to do that, first of all, we look at these types of pigments and we see that there are natural, synthetic, and mineral organic. And of course, I limit myself to the first of these, the natural mineral pigments. That is what evolved in our ecosystem. And we find out by looking at ancient works 45,000 years ago that the first pigment that was ever used, that we know of at any rate, was red iron oxide, first mineral pigment. And then looking at other more recent paintings, such as from the Rouffignac cave in France, which is 12,000 years before present, we are looking now at manganese pigments. But since manganese has many valences and iron only has 2, manganese is loose as a goose, and you also have lots of other oxides of manganese to play with, which the ancient people did. Now, if we look at the fact that iron is at the top of the binding energy curve, which means that it is pretty much the most stable nucleus in existence, it's no surprise that the entire sphere of the Earth has the highest concentration of this particular element. 32% of our Earth is made of iron, partly the core and partly compounds that were made with other elements. And we also find that manganese is very close to iron, both in stability and also in the periodic table. So here they are, and the other highlighted elements are other elements that actually give us some of the very beautiful pigments that we're used to. Now I'd like to call your attention to another element, and that is oxygen, up here in the upper right-hand corner. because oxygen is about 30% of our entire Earth, and therefore, since it's so abundant and since iron is so abundant, they've gotten together and they have formed, as you geologists know, the banded iron formations that you see here in the slides, and also have given to rusting of the earth and the red earth that we see that's so ubiquitous around the earth. Now, what we have to keep in mind, however, when we look at these pigments is that there were many more that eventually came into being, and that is, if we fast forward, say about many thousands of years ahead to the world of the ancient Greeks and Romans, we have a table here that consists of many more pigments, and these have all been taken from literature sources, the first two columns. The middle column, the analysis in the 19th century by Sir Humphrey Davy, and then the right-hand columns were modern analyses which show us this greatly expanded palette from ancient Greece and Rome. However, if we figure in the role of biology, which essentially is the role of oxygen on our Earth, and if we realize that oxygen was not part of the atmosphere at all until many billions of years had passed of the Earth's evolution, then if we take away the role of oxygen, which is basically the role of biology, we find that we end up with many fewer pigments. And if we look at the character of those pigments, they are simply the oxygen, iron oxides, manganese oxides, and sulfides. So where did these sulfides come in? This is a very interesting development, and if we look at the wonderful sulfide pigments that are available, we have, of course they're not lickable, remember, is we have mercury, the slide advanced too fast to go back. We have arsenic pigments, orpiment on the right, realgar on the left, and then mercury, which is in the form here of mercury sulfide, cinnabar, which is a favorite of the ancient Romans. They even painted their bedroom walls with mercury, and I don't think that's a very healthy idea, but they didn't know that at the time. Now you might say, where are all these sulfides coming from? Why is that so? And if we really look at the analysis of what was going on billions of years ago, what we find is that mercury wasn't really swift at the draw in terms of actually joining into mineral diversity such as beryllium. And we have a comparison here of the age of the Earth, and as it goes along with the continental formations, we see beryllium minerals. By the time we get to our own present day, there are about 100 or so beryllium minerals, but mercury was very slow on the draw and didn't start developing minerals until about 500,000 years ago, or 500 million years ago. There are only about 20 mercury minerals. And the question is, how come? Well, it all goes back to environment, because the oceans, the ancient oceans during that time was full of sulfide ion. And mercury and sulfide ion are like, they glom on to one another and form insoluble mercury sulfide, and that kind of puts mercury out of action, if you will. And so it really didn't have a chance to develop very many other pigments as long as there was a lot of sulfide around. So that's an environmental factor that has to be taken into consideration. Well, now we have to ask ourselves too, what's the role of oxygen in all this? Because remember, oxygen is mighty abundant in our Earth, and what we know is that it was tied up very much with iron and with manganese, but also with hydrogen in the form of water and with carbon in the form of carbon dioxide. But there was very little free oxygen floating around. In the early Earth, there was hardly any. We get to about a couple of billion years ago, and it's a minor component in the atmosphere. And only today do we know that oxygen forms about 21% of our atmosphere. So it wasn't very available to anything. And that is one of the reasons why we don't see too many oxygenated minerals, and therefore too many oxygenated pigments until very late in the life of the Earth. So if we take a look at this figure here, what we see is that oxygen was non-existent as the element in the atmosphere 4 billion years ago, and it gradually began to grow in concentration until it reached our present level of 21%. But this is a logarithmic scale. So remember, there wasn't very much oxygen at all until we get up towards the top of the scale here. And you might say, well, how did this all happen? And the answer is these little critters that are called stromatolites, or they actually are cyanobacteria, which learn how to carry out a very important chemical reaction, namely photosynthesis. So if we go on to the next slide here, what we see is that when that happened, excuse me, back one. All right. Sorry. All right. What we see here is that as oxygen begins to develop here and life begins to develop, the number of mineral species, which is the left-hand axis, goes up. And by the time there's a fair amount of oxygen in the atmosphere, we now have quadrupled the number of mineral species from early Earth. And so this is a factor that's very important, and of course one that was brought about mainly by these stromatolites, because what they're able to do, they actually found the secret of taking water and pulling it apart to get electrons and hydrogen ions, and then using those to act upon carbon dioxide and reducing it to nutrients in the form of carbohydrates. Of course, this is the classic photosynthesis reaction, and you notice that oxygen is a waste product. It's produced in photosynthesis. And you might say, that's how we got oxygen in the air. Well, not so fast, because all living creatures have to respire, they have to breathe, and that's the reverse of photosynthesis. So it's a zero sum happening here, photosynthesis, respiration. However, if indeed what they have produced by photosynthesis can be sequestered, namely if by sedimentation and upheavals in the crust of the earth, the organic materials can be sequestered so that they cannot breathe, that is when oxygen can then accumulate in the atmosphere. And so essentially, as it accumulated, the number of mineral species, and therefore the number of pigment species, actually quadrupled to the present stage. And so the bottom line is that the biosphere and the geosphere evolved together. And this actual thought is a paradigm shift in geology that only began to take hold maybe about 15 years ago. And so it's something that still really has to be explored to see if we can say that this might be something that is a new model of evolution. And this is what gives us now are beautiful pigments that are oxygenated pigments, because although for ultramarine blue, the chromophore is the trisulfide radical anion, it doesn't shine nice and blue unless it's in this cage-like structure, which is highly oxygenated. So it would not exist without oxygen in the atmosphere, and therefore would not exist if those little stromatolites hadn't begun producing the oxygen. And all of this is a very complicated question that chemists have been working on for many years. Here are some others that we have. Raphael Sistine Madonna has, malachite green, gorgeous copper carbonate, oxygenated pigment. We now also have azurite, or an Armenian type pigment. And here's beautiful blue in this Armenian manuscript. Again, a basic copper carbonate. And here's another bunch of oxygenated pigments that we have simply because of those little cyanobacteria. And so we come to the end where we have all this diversification, but now we enter the anthropogenic era right here, and what we see is a growth in other pigments, mineral species, because of the work of human beings. And so we have to ask ourselves, is there an end to this? We don't know. We really don't know. But at any rate, I think you have a lot to think about now, and here's a lot to read as well. So I would suggest that you take a look at this list of books and of articles, and then thank you very much, and copy down quickly my email address, maryvirginiaorna@gmail.com, and I will be glad to send you a copy of these slides in which you will have reading for the next 14.7 billion years. Thank you very much.
Dr. Sister Mary Virginia, thank you. It's really an eye-opener to understand the important role that oxygen played in the progression and evolution of the Earth and how it affected chemistry and why we have the pigments we do today. So thank you for taking the time to prepare that. Incidentally, I learned
Chapter 5 in my book brings that out as well. It's all about mining and geology. So I think you geologists would enjoy chapter 5.
Excellent. I learned when we were doing this, preparing for this webinar, that Dr. Sister Mary Virginia had direct access to some of the most sensitive artwork in the world, partly because of her well-respected research in chemistry and antiquities. And during COVID, she told me that she wrote this book. It's over 450 pages, 15 or 16 chapters, and it is a masterpiece treatise on the combination of history, chemistry, geology, and pigments. I don't think there's a book like this. So if this is your interest, this is a book you don't want to miss. Before we move on to the next slide, I just want to shout out to somebody who I can't forget. Chip Munsell is logged in today from Elkhart Lake, Wisconsin. Hello to you, Chip. Next slide, please. I get the distinct pleasure of inviting everybody to the AAPG Women's Network. If you're already a member, you already know the benefits, and there are many of them. But if you're not a member of AAPG Women's Network, join now. There is a link that's going to be hitting you right now via the chat message. All you have to do is just register, put your information in there, and then you become a member right away. It is definitely leadership in the women's AAPG and in all geology disciplines. It's a very active organization. There's many volunteers at many different things that they do, many upcoming events. You can make an impact with a very unique mentoring program that's powerful for the people who are seniors and seasoned professionals to be able to help entry level and upcoming professionals as well. So don't miss this. There is also an upcoming very important session about carbon capture, utilization, storage, and you don't probably want to miss that. So if you have any questions, contact Allie Sloan. Her email's on the lower left of that slide, along with Mary Virginia's. It will also be available after the webinar as well. Next slide. Chris, if you'd like me to just mention this, otherwise, Chris Pala, who's on this webinar, she knows a lot about what's going on with this, but May 5th, you don't want to miss Women's History Tour of Houston and a networking social at the Pure Noir Winery downtown Houston. So don't miss that.
Screenshot it real quick if you want. If you're in Houston on the left-hand side, there's 7 tour tickets still available. And then screen grab the right-hand side if you want. It's the same email, awglonestar@gmail.com. Our annual field trip this year is to Palo Duro Canyon, which is the Grand Canyon of Texas. So just, screen capture the email if you're interested in the field trip, send us an email and I can give you more information. The pricing is variable depending on which cabin you choose and how many people you decide you want to split it with.
Excellent.
Thanks, Dan.
Thank you, Chris. Yeah, and up next, please help me welcome our next panelist, Chuck Hoover.
Thank you. Thank you. My family has been making pigments for a little over 100 years. And I think my first pigment job was when I was 5. So I've got a little experience. The color industry is a little odd. You know, the people who make white don't make black. The people who make red don't make blue. My family makes what are called iron oxide pigments, which are basically, you know, your earth color range of browns, tans, yellows, reds, blacks from there. Next slide. So one of the things that I want to convey today, and if you go away with anything, is pigments and dyes are not the same thing. You know, when we talk about color, most laymen use those terms interchangeably. Next slide. But there is a big difference. And the difference is dyes are soluble material that have a certain affinity to bind to a substrate, whereas pigments are insoluble particles that must be glued together or glued onto that substrate. Next. Of course, there are some innovative people out there who figured out that you could take inert material like kaolin and dye it, and we call those pigments lakes. Next. So if we talk about the pigments, we typically break those down into those based on organic chemistry and those based on inorganic chemistry. And for the most part, the mineral-based geologic pigments are in the inorganic range, although there are things like lignite, you know, that are the predecessor of coal and coal itself that can be used as pigments. Next slide. So if we talk about something like a colored t-shirt, you know, we know that that t-shirt has different feels. And really the fabric itself is colored with a dye that has an affinity to the cotton or the fabric that the t-shirt is made on. But you can't get that precise design and wording in there with a dye. So they make, you know, basically a paint, we call it a silkscreen ink, that glues the pigments onto that t-shirt. Next. You know, so I'm going to step back and strictly focus on, you know, the mineral-based colors out there. And really, when we go to our basic geologic training, you know, one of the first things they teach us about mineral identification is the streak test. If you don't have a good streak, you know, you're not going to get any color out of the rock. So, you know, that is really kind of the first test of when we see whether a mineral has any pigment value. Next. The other thing that isn't quite as obvious is the hardness. We really are talking about pigments reflecting light, so they need a large surface area. You know, personally, I really don't think that, you know, anything really is a pigment until it's below 10 microns in particle size. And, you know, an average human hair is about 100 microns in particle size. And so, you know, some pigments throughout the ages are based on their hardness. Next. You know, for example, the oldest known pigments that people have been using are about 70,000 years old, that were found in South Africa. And even back then, people realized that you had to grind these pigments up to maximize the surface area. And this is a 70,000-year-old mortar and pestle. And again, Cristina is using a muller, and that's basically what she was doing with between the pigments and the vehicle, is dispersing that pigment out so it has a maximum amount of surface area. Another interesting thing, next slide, that our prehistoric predecessors figured out was that iron hydroxide plus heat changes the chemistry of the iron from a hydroxide to an oxide, which in that recrystallization changes it from a yellow undertone or yellow color to a red color. So if you know some of the artist terms, raw sienna, burnt sienna, raw umber, burnt umber, actually you're talking about, you know, converting from the yellow color to the red color by heat treating. Next, so if we look at a prehistoric palette, and this is just kind of a combination of all sorts of cave paintings that have been done around the world, we can see that, you know, the prehistoric man was using, you know, gothite yellows. He was heat treating it and changing it from a raw sienna form to a burnt sienna form. We see that he was using hematites, although back in the early days, it was probably hematite mixed with clays to produce what we call an ochre. He was using different types of whites, either calcium carbonates, primarily calcium carbonates, in the form of chalk. And then the blacks, as Mary Virginia said, you know, you had iron that had manganese substitution in it that produced a very, very dark brown that was almost black, your raw umbers. And the other thing that they used was bone charcoal. And we still call that bone black or ivory black, that was used to, you know, do a lot of the outlines. Obviously, the charcoal end of a bone was a good pencil in your prehistoric days. If we move ahead, next slide, you know, colors were traded throughout history. One of the most, you know, we've already referred to some of the lapis blue that was mined in Afghanistan, or what we call Afghanistan and Pakistan today, and was carried throughout the world, you know, back to artists in Europe. One of my favorite little references is the wealth of the patron of painting in Renaissance and medieval Europe was the amount of blue in it. because blue was more valuable than gold at the time. And so especially a lot of the Dutch masters would always have like a little blue window in their painting, and how big that blue window was how wealthy the person they were painting was. Next. If we look at some of the minerals that are associated with their colors, whites, the most common white used today is titanium dioxide, which is based on either rutile or anatase. Before that, there was leads and zinc whites. The blacks were either iron or copper chrome. From a mineral standpoint, there was also the charcoals and things like that. Reds, oranges, and yellows, cadmiums and irons, greens, copper and chrome, and blues. Yes, you got some copper in there, but cobalts, and again, the lapis blue, which is a sulfur anion substitution in sodalite silicates. The chemistry that's near and dear to me is your iron oxide chemistry. Again, as Mary Virginia said, hematite red is kind of the most stable mineral out there. And we see that coloring everything from the Grand Canyon to, your red rubber balls, your red erasers on your pencils. Goethite is the iron hydroxide that's common. The black, there is a black that's used as pigment, magnetite. Really, because of its hardness, it wasn't used until later on when we've improved our grinding techniques. But today, magnetite is a common black pigment. Umbers and siennas are your yellow goethites with a certain amount of manganese substitution. Most people don't think of an umber, which is a dark brown, as a yellow, but from a mineral standpoint, it's a goethite that has manganese substitutions. And then the artist term ochres are usually hematites or goethites that are contaminants in clays or carbonates. Next. Many of these pigment minerals are associated with hydrothermal activities. We had a question already on mine sources. And while you can find mineral pigments in almost, any rock, finding an abundance of the material that you're able to mine is pretty unique. So a lot of the deposits that we work with are associated with metal deposits and are the result of hydrothermal activity. Next. But you also have colors that are formed during volcanic activities. This is terra verte, which is a form of bentonite that has a high copper chrome content. Next. Throughout time, there's been an evolution, as I was talking about a minute ago. We've improved our ability to grind pigments. We've also been able to improve our ability to extract contaminants. So the most, probably 90–95% of the white that you see today is based on titanium dioxide. Yet, it's only 100 years old. So before that, they used lead whites, zinc whites, and the rutile and anatase is contaminated with iron. So until you were able to extract that iron, you didn't get a bright white color. So a lot of times if you're looking for, like, say, paint forgeries, you know, they'll be going back and looking at the pigments and see whether, you know, were those pigments available when the painter lived. And, you know, again, this Claude Monet, you know, if you had found titanium dioxide in it, you know it would be a fake. So my last slide is, you know, pigment frontiers. We all know that Mars is the red planet, and the red comes from iron oxide. So I think the shipping costs are going to be a little expensive, but, you know, as we go out into space, we will still be able to find mineral-based pigments out there. So thank you for your time. I'll answer questions at the end.
Great. Thank you very much, Chuck. We're going to stop sharing real quick because we're going to do another painting session. Let me go over to Christina's camera. Great. And while I've got
And the cat came back.
the cat's back, yeah. The back of the cat is back.
Can you
While I've
hear
got
me now?
an unmute, yeah, just one moment. I see some people raising hands. We're going to do some Q&A at the end where I'll be able to unmute people if you want to ask a question live. But in the meantime, please put any questions in the Q&A tab, which is on your Zoom ribbon near the chat box or near the chat icon, or put any comments in the chat. So, sorry, take it away, Cristina.
All right. So in watercolor, the other thing that's very common is to do different washes, also called glazes. So what you do is if you want to make a color, you know, let's take Bob's Environox Raw Sienna. We want to make this a little bit more bright. Then we'll just do another thin layer of that golden color. On the other hand, if we want to make it a little bit darker, we do another layer. Rather than pile it on, it is best with watercolor to let one layer dry and then go back with a thinner layer, and that's called glazing. And that allows you to give also some dimension by having some parts be darker and some parts be lighter. The other thing is when you do this, it's best to leave some of the bits of the earlier wash visible. I like to think of it as a painting that tells its own story. It shows you the different phases that it went through before it came into being. And it's just nicer to have this second layer. And you can do that with most of these. Same with the pear. See how nicely that area of light came because I used we call it a thirsty brush. When it's damp but clean and your paint is still wet, and you just kind of lift it, and then you have a return to the white. Some synthetic colors don't let you do that. Those are called staining colors, but most earth colors you can lift. You know, they're gentle that way. They can be very powerful and yet at the same time gentle, just like many of us would like to be. So as long as things are wet, you can mix them in. I want to leave this white because I'm very happy that it stayed, and maybe make this so yeah, I'm sure Bob's going to talk about this, but I don't know if you notice, when you look at these pigments here, they look very similar, but Bob's iron oxide are just really strong. And I call it, like, if you have a little half pan, it becomes a lifetime supply, which is really great news because the paints can be so expensive. Now this is still wet here. And another good term that we use a lot in watercolor is happy accident. This didn't dry the way we would like, and it's still wet. So what I'll do is I'll just turn it this way, pretend this is the sun, and it looks kind of nice that way. And then since I live by the lake and I live near Camel's Hump, I can make, remember that was the first wash we did, right? So I could make with the second wash the outline of Camel's Hump on the lake. So here I have that dark, and I'll make it darker on this side because it's farther from the sun. And then using the light, I can do a little sense of lake waters. It's simple, but it's a very relaxing way to paint.
And I like that you're drawing geology or painting geology using geologic paints.
Yeah, should we really paint
It's very
geology?
meta.
I was gonna do something else and I thought we wouldn't have time, but I love to paint rocks. And when Stefano visited, here they are, Lake Champlain, I don't know what these are, you guys know, but there's a lot of these stones that have a line through them. And when the kids were little, the legend is that if you find one that has just one line and it goes all around, then we call it like a wishing stone or something. They have magical powers, as we all know as science people. So this is fun to do too. You just do, because with watercolor, I meant to say this earlier, if you have two colors, you really have three colors. It's the two colors plus the white of the paper. Watercolor, unlike most other paints, does not have a white. You can buy, you know, titanium white, zinc white. It's not that it doesn't exist, but it's not like if you participate in serious watercolor competitions, that's not allowed, because traditional watercolor artists are supposed to use for white, the white of the paper, which we see here. So here too, I don't have gray here with me. So I'm just using the colors I have, which are beautiful. Do you make black, Bob? Maybe you can answer that question later. I would love that. And there's a geologic formation for you. I don't know if you're interested in seeing some of the, Mary Virginia spoke about certain minerals. For example, this is a tiger eye, and this is a tiger eye pigment. I collect pigments among other things. So this is the beautiful blue lapis lazuli, and this is the lapis lazuli pigment. Now, as you can see, lapis lazuli is not just blue. It has white. It has other things like calcite and sodalite. So to get just the blue, it's a big process of squeezing it out of. I've seen people do it. You can do it on YouTube, watch it on YouTube. But in addition to being fairly rare as a blue stone, it's also very difficult to extract, very time consuming, which is one of the reasons why lapis is so expensive, but it is also very beautiful. So I hope you will play with your pigments. I will show you one last fun thing that you can do with paint. And that is, and you can do it when it's still wet. Get plenty of water on your brush and on your paint. And then you do this. We call it spatter or splatter. And it gives us, it's fun. If I paint birds, it looks like feathers that are flying every which way. And I know that I keep saying it's the last thing, but this really is the last thing. I want to show you two other pigments. These are the one closest to my house and the one farthest from my house, and you will see why. The one closest, a friend of mine made pigment out of a pebble / brick that I found on Lake Champlain in my walk 10 minutes from my house. And this is the closest one. The farthest one I bought at the most reputable pigment company. It's called Kramer's. And this is meteorite. They ground into pigment a piece of meteorite found in North Africa. It's very, very expensive, as you can imagine, but it's out of this world, as one might say. So thank you for playing with me, those who did. Stefano, you didn't paint. I'll get you
Awesome.
painting soon.
All right, I'm going to share the slides again. Thank you, Cristina. And Bob,
you.
go ahead and take it away.
Okay, well, thank you very much. And that was just fantastic, Cristina. That was really cool. So I am not a geologist. I'm an ecologist, and but I hang out with a lot of geologists because my career has been in the treatment of contaminated mine drainage. And being an ecologist, I do it in a passive way. So I'm very natural in the approach we take. And we've had a lot of success building a lot of systems. Go to the next one. And so, you know, my one chemistry slide is that this is sort of what my career has been in Hedin Environmental, which is a small consulting firm. There's 8 of us. That is the basis of what we do is we deal with the sulfuric acid and the dissolved iron that's produced when pyrite is oxidized as a result of the disturbance of mining activities. And when we do it right, we neutralize the acidity, which we're not talking about here, but we also take that ferrous iron, that Fe+2, and we turn it into a solid and collect it in a treatment system, in a pond or a wetland. And we do that through natural oxidation processes. We do it through biological microbes get involved in this. And we actually, whenever we do have acidity around, we try to use either microbial activity or limestone as a natural neutralizer. And this is a very successful, technology. It was developed first about 30 years ago. And there have been hundreds of these installed in Pennsylvania, where I live, and thousands worldwide, these passive treatment systems. So next. So here's what a passive treatment system looks like. And I don't have to tell anybody what's happening here, other than that there's a lot of iron being formed here. And so the water is flowing out of an underground coal mine. This is in Western Pennsylvania. It's flowing out of an underground coal mine on the right-hand side of the slide. There's a parking lot there because this is a popular site, people come here and do things here. And then it flows serially through these ponds, through these 6 ponds, into a shallow ponded wetland, but there's no vegetation in there. It's just about 1.5 foot deep. These ponds are all about 4 feet deep, and then flows back and forth through a constructed wetland that you can see. We have berms in there to make the water flow, and you can see, because iron is pigmentary, you can see the flow of the water, but it gets to the end, and the very end is the end of the system is on the very left side of the slide, and you can see it's clean. And in fact, the chemistry, analyses verify this. We've got 70 milligrams per liter coming in on average and about 1 milligram per liter coming out. That's actually a little high because I only take samples when it looks bad. When it looks good, because I go by the site often, I wouldn't bother to take a sample. You can see this is different than this kind of iron oxide forms in systems that are alkaline in nature. And so it's kind of a misnomer when people say acid mine drainage. Yes, there's severely acidic mine drainage, but there's also a lot of alkaline mine drainage because of all the interactions of that mine water with carbonates and silicates underground in the earth, and the discharging water in this area, in this part of Pennsylvania, the deep mines that are around here produce alkaline water, pH in the 6s, which by the time you get to the end of the 7 is pH in the 7s. So what I want to point out up also, because we're going to zoom in on it, that upper right-hand portion of the treatment system next to the parking lot there, that actually is piles of iron oxide that have been recovered from the system. So next slide. So if you know, this is a great technology. It's passive, really very little gets done here other than check on the system. And if there's muskrats in there, maybe you have to deal with the muskrats. If there's leaves and sticks that have plugged up a flow path, you got to remove those. But it is passive, just like you think, just like the word says. But the thing is, the ponds, if it's effective, the ponds fill up with iron sludge. And eventually, it won't work as well because you won't have the retention time because of all the solids in there. So periodically, you need to go in there and you have to remove the sludge. And we do that at this site. So we literally just pump it out. And we put in infrastructure here, pipes that allow us to bypass water around individual ponds while we're doing a sludge removal activity and still maintain treatment of the system from the rest of the ponds in the wetland. And this site, you know, usually if I have my druthers, we would pump the sludge into a pond, a sludge basin, because that's the cheapest thing to do, and let it dry out, and then eventually remove the dried sludge and use it all over again. This site, we didn't have that opportunity. We used pretty much all the property to build the treatment system. So what we do is we pump it into something called a geotube, which is a geotextile pillow that you pump solids-rich water inside of, and the water leaks out through the webbing, the fabric, through the woven fabric, and the solids get retained inside. And so that is a geotube on the upper left there. That is when it's full. It's well, that geotube is 60 feet wide by 120 feet long. And when it's full, when we filled it up, it was about 8 feet tall. Over time, the water comes out, and eventually it gets to the point where we can actually cut the top off the geotube. You can't reuse them, unfortunately. And that picture on the right is one of several of the geotubes with the top cut off. And now you can see what we have inside. We have iron oxide, and it's starting to dry. That cracking is what we like to see. That means it's drying naturally. We're passive. I'm a passive guy, so we use just weather to do this. Eventually, we get the iron oxide to the point where we can stack it up, and you can windrow it like you're seeing on the bottom left-hand side there. And then eventually it goes into a truck and most of it goes to Hoover Color Corporation. And so this process, actually, this idea of recovering the iron oxide and producing a product from it, this started from a proposal I wrote to the Department of Agriculture 30 years ago, and 25 years ago. And part of that proposal was, I think, you know, we're making pretty pure iron oxide in these treatment systems. Maybe I can find a market for it. And so a big part of the proposal was to send samples of the material to anybody I thought could use it. And the only response I really got was from Chuck Hoover. And that was wonderful. And Chuck, it turns out, didn't tell us about it, but he has his family owned an iron oxide mine in Virginia. And apparently this material competed very well with the material he could mine out of his iron oxide mine. And so I got an interesting phone call from Chuck one day saying, yeah, this looks pretty good, Bob. Could you send me 1 million pounds? And we were in the rate at that time, I had buckets of material. So that changed, a lot of things changed that day when we had to figure out how to make a lot of material. And it took us a few years to figure out how to do it. But this is the material that now it's collected. We've developed a good process here. And what you can see, here's an analysis in the bottom of the elemental content of that sludge. And what's, you can see it's iron. It's 53% iron. What's missing is what you see there, a little bit of aluminum, a little bit of calcium. You see a little bit of calcite form in these systems. The rest of the weight is O's and H's, because it's, as we just saw, it's ferrihydrite, which is FeOOH. So there's a lot of O's and H's here. But so that is awfully pure goethite is what that is. Next slide, please. And so we've seen this enough times, but this is what Chuck taught me is that what we're making is a goethite or goethite. We're making a sienna, and you heat it and you turn it into hematite, and you have got your two colors there. And actually, this is kitchen science here. That iron oxide is obviously from one of our piles, but the heating, you can do that in a toaster oven on broil. So that is how we actually, the materials that Cristina got from me, they were fresh out of a toaster oven the day I sent them to her, the reds. Next slide. So one thing though that's special about Lober that Chuck and I really don't understand why is what a good pigment that system makes. And these are color drawdowns. I think that's the right word. I should let Chuck eventually come in here and talk more about this, but this is looking at, he could explain, in fact, Chuck should explain what's going on here. But what I want to point out right away is that the Lober material is a much darker color than the Wilson and the St. Vincent, which are also iron oxide sludge deposits, very pure, equal purity from passive treatment systems in Western Pennsylvania. But the Lober material is special because of that good color. And Chuck, are you able to just sneak in here and tell us what these are telling the crowd?
Well, a couple things. So geologically, from why we switched from the mined material to the iron oxide material is if you think about the deposition environment of our mines in Virginia, we had lots of contaminants. You know, we were close to a coastal plain, so we get sand, we get clays, which all dilute the color. Where Bob's process is produces a much higher purity material. Now, what we're seeing here, the differences in the color, have to do with how well the pigment particle grows. And I saw somebody had a question on purples, and as far as iron chemistry, we do get into some of the maroon colors, as you see the Wilson Pond here, and that is actually a bigger crystal, hematite crystal, than you've got in the Lober material. So the Lober material is kind of our sweet spot. We can do a lot with that. You know, the darker it gets, and as you see, the intensity also goes down to the left. You know, you don't have as good a color value or tinning strength with the Wilson Pond as you do with the Lober. Back to you, Bob.
Okay. Thanks, Chuck. Okay, so, you know, that was 1990, that was 2000 when Chuck and I had our first discussions. And so what came out of it was, as we heard earlier, I think my last tally was about 3,000 tons of solid of iron oxide has been produced from that site and from other sites. And most of it has been shipped to Hoover Color, gave it a name. You know, I was typing one day and I realized, holy cow, environment has iron in it. So we had to give it a name, environment oxide. It appears, this is me speaking here, but as Chuck just said, this material is cleaner than what normally natural iron oxides are, but it's not as good a pigment as synthetic iron oxide. So we seem to be in the middle a little bit there, in the middle there of the naturals and the synthetics. And, but that makes good pigment. And so it's being used, wood stains, paint, concretes, and plastics. I thought I'd show you some examples of what it's being used for in Western Pennsylvania. So next slide. So first thing, we like to do tie dyeing here. And we've got, it's not like your fancy, you know, colorful pigment. I guess those are dyes, you know, those dyes you use in tie dyeing. This which is tie pigmenting, as Chuck pointed out to us. That's my son there with the gloves on in the front, and that's his wife, Chloe, in the back. I think I'm on this because Chloe, they're both PhD geologists and from the University of Pittsburgh. And I think that I'm here because she's a member of the group and she recommended that this would be a neat topic. And you can see why she's into it. They're making all kinds of tie-dye t-shirts and you can use both colors. So it's a very popular thing. Earth Days are coming up and we're going to be doing a few of these on Earth Days. Next one. Next slide.
I'm on the house slide. You see that one?
Okay. Yeah, the house slide. Okay. This is the burnt sienna pigment that actually I just gave them, I believe, some burnt sienna and they mixed it up. This is a natural plants horticultural place. And anyway, this is painted with pigment made from the burnt sienna. Next. So a big use of iron oxides is in construction products. Well, that's a construction product, but in concrete. This is actually this is part of the Allegheny, it's the rails to trails from Pittsburgh, Pennsylvania to Washington, D.C. There's a long bridge. There's a couple long bridges and they had to replace the deck on it. And this happened about 15 years ago when the whole idea of making pigment from mine drainage was really getting a lot of attention. And so they actually pigmented the concrete with iron oxide from Hoover Color, which was ultimately the iron oxide from the treatment systems in Pennsylvania. So a lot of iron oxide can go into this. Next.
We're on the table. I think you got a
Must
little
see
bit of
me
a
yet.
delay. Yep.
Okay, that must be me. Oh, there's the table. So this is our picnic table in the backyard. One thing that Chuck told us is that a lot of the burnt sienna was going into wood stain, dark cherry wood stain. So we got ourselves a cheap pine picnic table, and my wife and I, we mixed up some burnt sienna stain and made a beautiful picnic table. So that's apparently, if we want to hear about it more, I think Chuck says a lot of the Lober burnt sienna goes into wood stains. Next. And lastly, what Cristina has done here, actually it's just a pure coincidence, but we're up where I am in northwestern Pennsylvania. There's actually a conservation district that's very involved in building and maintaining passive treatment systems that accumulate iron. And the woman in charge of that linked up with the local artist, and they're actually teaching a course now about using locally sourced iron oxides for watercolor painting. And this is, I can't show you my painting because it looked like it's from Mordor. But anyway, this is my wife's painting. And so it's pretty cool. We got, 30 people in a room mixing up iron oxides from the mine drainage treatment systems with some carbon black in there as well. They needed some black. And the same question as Cristina was asked to me, can you get us black, Bob? And I'm on the search for a good, clean manganese oxide, which is a very black material from our treatment systems. But anyway, I can see that this idea of doing t-shirts is a wonderful idea, tie-dye t-shirts, but the idea of painting with it is even better. So thanks so much for that. Next one. I think that's it.
Yeah, that's it. Thank you,
That's me.
Bob, and thanks to all our panelists. We're going to have some Q&A now. So Chris, if you want to unmute, I'm going to stop sharing so that we can see our
That was
panelists.
wonderful. That was awesome, you guys. Oh my gosh. I was so excited. It's the best one yet. Everyone that we have is the best one yet. Okay. I tried to warn the panelists. I tried to send them some questions as they came in. So we have one. How does purple form? We have purples from Puerto Rico that we use for watercolors from soils that are really, really eroded.
So those are basically a large particle red iron oxide, which is more of a maroon color than what we would consider a barn red. The classic American barn red is a red hematite, And in different places, the particles grow differently. The warm temperatures in Puerto Rico probably allowed the crystallization to take on a little longer and grow a little larger particle, which produces a more purple color.
Cool.
Perfect. Thank you. The second question, do pigment scientists analyze the images from Mars to suggest mineralogy? I would guess that they actually have physical samples they're analyzing. What do you think?
Well, we actually, when they put out an analysis of Mars rocks, we compare that to, what we're getting now, and the same thing on deposits from the mid-Atlantic ridges. We are able to take a look at that chemistry and compare it to, chemistry that we currently are working with and determine whether, you would have pigment value.
Very cool. Yeah, I think you're right about the shipping costs though from Mars. Bob, do you need to monitor the passive treatment systems in perpetuity, or what's your monitoring situation? You just grab samples when it looks awry?
No, they should be monitored, every few months in perpetuity, as long as the mines are putting out polluted water, which that deep mine will be putting out iron-rich water for many lifetimes. And that is something that's up to, and that system is run by the Swickley Creek Watershed Association. It's a volunteer group, works closely with their conservation district, and they monitor it periodically. And luckily I'm around, so I'm there to watch and keep it going. But the sludge removal activities, the cleanouts, that's going to have to keep going every 3, 4, 5 years. Every 3 to 4 years, we're going to have a sludge removal activity. Just have to hope that we can keep sending that down to Hoover Color. That's what our plan is.
I don't remember the particulars, but when we first started the pilot plan out at St. Vincent, the chemistry department at St. Vincent College had done some analysis, in like the 1960s. And, the iron content of the acid mine drainage compared to the 1950s, compared to what we're getting now, or when we last looked at it, Bob, was very, very similar. So, we're assuming that it's a ongoing purity that we can collect in perpetuity.
One more question for y'all, and then we'll switch to some questions for Cristina and Sister Mary Virginia. Can you purchase the Sewickley Creek watershed pigment?
Yep.
Well, you can from Hoover Color / Oxide. There has been a little change of the name. I don't think you're going to get, if you want to do what Christina's done, you just email me and I will be glad to send you a baggie of sienna, and you can turn it into sienna and burnt sienna pigment. If you want to paint your house, then you're going to need to go to Hoover Color or Oxera, and actually buy the dried pigment, or Chuck can tell you where you would go to find it in finished pigment. I'm not sure where you go get finished.
Well, most of your artist paints, if you see the word raw sienna, burnt sienna, most of that is made, based on an environment oxide. Cristina, where you bought the American-made burnt sienna versus the environment oxide, the difference that you're looking at is that we have blended the environment oxide with other materials to match the historic mined material that we used to mine in Virginia.
It's the end of an era.
Yeah.
Yep. You ran out. Okay, Cristina, this might be for you. Is fine grinding malachite, azurite, and turquoise practiced for greens, blues, and light blues? And there's another question that's kind of in line with that about color. Are there any reasonable green mineral pigments, and are they relatively easy to come by? So the first part was, is fine grinding of malachite, azurite, and turquoise practiced? And then as far as reasonable green pigments minerals.
Yes, it is practiced, but I've made, and I can show you, malachite comes out great. Azurite, I haven't been able to find good azurite, because what happens with azurite, as with many pigments, if you grind, also tourmaline, if you grind them very, very fine, the gemmier, I don't know if that's a word, gemmy, when it's very sparkly, it doesn't come out as brightly colored as in its crystal state. So with malachite, they can do it. With lapis, they can do it. With azurite, it's always a little bit too grainy for my taste. Greens, somebody mentioned the terre verte, the terra verde. There's a lot of natural green, the celadonite from Oregon. It's just, again, hard to get like a strong green. You'll get a pale green, and it's beautiful. But when Mary Virginia showed the picture, the painting of Raphael Madonna with that bright green, I don't know how they got it, but if you grind malachite, it's not going to get that dark. So they must have done their own little chemistry thing, or cooked things up in their pizza oven or something, because it's not easy. So the one of the problems, I don't know if I should talk about this, but I will. Daniel Smith, which is one of the biggest producers of watercolors, and they're based in the United States, and they make beautiful paint. However, they came up with this line of paints called Primatech, where they claim that they are made with original genuine gems. They're much more expensive than usual, lower tinting strength. People buy them, and from when I first started making paints, I'm like, there is no way. You cannot get bright purple with amethyst. You can grind the amethyst as much as you want. You're not going to get bright purple. Recently, one of your people, the scientists, on this was a big deal because she has a very highly followed Instagram account, Ruth something or other. She used a special microscope that you use for this purpose, and I can't even remember what it's called. I wrote it down somewhere. But she proved without the shadow of the doubt that there's no amethyst in Daniel Smith's genuine amethyst. There's a whole plethora of things that they claim that, to me as a paint maker, was clear that they were not truthful. And they wrote to Daniel Smith, and Daniel Smith was very evasive and rude. And basically, you shouldn't really buy those paints thinking that they are, the bright green. So they'll sell Sleeping Beauty turquoise made with genuine turquoise. And I've made paint with turquoise, and it comes out, it's beautiful. It's beautiful, but it's very pale. It looks like the table of contents behind Mary Virginia's head, but like a few shades paler. So when
There's a
somebody
reason
tells
for
you
that.
something, when it sounds too good to be true, it probably is. Meaning it's a good thing that we have synthetic pigments for, like,
For some colors, yeah.
right.
Well,
It's probably a scanning
Tim-
electron
Amount of
microscope.
pigment, the paler it gets. And the reason why is because as you grind it into smaller and smaller particles, the light gets to scatter more than it would for coarser particles. It will scatter at more different angles, and therefore the reflection back to your eye will be very diffuse. And that is the reason why pigments that are ground down to a fine particle size are extremely pale. And it has to do basically with the phenomenon I just mentioned, scattering. It's called Rayleigh scattering, and it actually depends upon the fourth root of the frequency or the wavelength of the light that is striking. And unfortunately, visible light behaves in that way because of its particular frequencies. And so there's nothing that can be done about it. You simply have to have a coarser mineral pigment, but it doesn't stick very well then to your surface. And as a matter of fact, the people that painted medieval manuscripts had rather coarsely ground pigments. I've analyzed a number of medieval manuscripts, and there's a problem to that, because when you open the pages of the manuscript, often the pigment particles will simply fall off and fall into the gutter of the manuscript. And so there are a lot of places on the manuscript that are pigmentless, that had pigment on them because they used coarsely ground pigments, which were very beautiful and bright, as you saw in that Armenian manuscript. But there's a payoff there. You really can't get the pigment particles to stick very well. And even if they stuck, sometimes when you close the pages of the manuscript and they're closed for several centuries, and then you go and open the pages, some of the pigment will stick to the opposite page, and that's called an offset. And of course, that's a disaster as well.
All right. And that's a problem also if you work in sketchbooks, because you have it on the other page.
Of course, you also have another problem, and that is some of the pigments would decompose, like the copper pigments will decompose over a few centuries and actually turn brown, and not only that, eat holes in the parchment. And sometimes the holes can eat through as many as, dozens of layers of parchment.
And the other problem with azurite is that sometimes I've made it before and it's beautiful, and you paint it with it and it's a beautiful blue, and then it turns to malachite for some mysterious chemical reason, so that after a few months, what was blue, it doesn't even take centuries, it takes weeks, months, it becomes greenish.
Well, actually, those two colors are extremely related to one another. They're both basic copper carbonates, and the color depends on the degree of hydration. So you change the hydration. Of course, is simply by if there's some water that is evaporated or added. In either case, you get the change in the hue.
Yeah. Oh, well, it's not magic then. It's chemical.
No, not magic at all. It's water.
Well, I wanted to take a quick pause and just thank our wonderful panelists for their participation and presentations today. We're a little bit over on time, but on the official program, but we're going to stick around and do a little bit more Q&A. But thank you all very, very much for participating, and thank you to all of our attendees for the awesome Q&A and comments in the chats. You'll be able to go back and watch the recording, of course, to capture anything they might have missed. And there's been lots of emails and links shared in the chat window as well. So if you haven't taken a look there, please do so. I notice we have 3 hands raised, and I'm going to click on the first one that I recognize. I think you were first, Victoria. I'm going to click on allow to talk, and let's hope this works. So ask to unmute. Go ahead. If you would like to ask a question live, I'll give you a few seconds. If not, I'm going to go to William Dupre. and I clicked on allow to talk. So if you, oh, I see William's unmuted.
Sure.
So go ahead.
Okay, thank you. When you look at desert paleosoils, you often see a spectrum of greens and purples and reds and yellows. And I've been told it's a variation in the oxidation state. What exactly is causing that variability in the soils of desert paleosoils?
I think you've said it. It's the oxidation state. You know, whether you're getting a hydroxide or an oxidation taking place. You know, it just varies. Again, particle size of, let's say, your hematite will affect your shade. So you're talking about your ancient environment, you know, how warm things were in those soils, and when, you know, where the crystallization was taking place.
Great. Thank you for answering that. Victoria, if you're able to unmute, go ahead. If not, I'm going to wait a moment and allow Anna Vargo. Whoever unmutes first.
Sorry, I don't.
Anna. Go ahead. We can hear you, but a little bit of echo.
Sorry, I didn't realize I raised my hand.
Oh, okay. No worries. So, Victoria, were you able or not? Yeah, here we go.
Hi, this is Vicky. Can you hear me?
Yes.
Mhm.
Go ahead.
Hi. Bob, I just wanted to say it's really fascinating. I work in the mining industry in Illinois. I'm a state regulator. So, and actually, I think I've been to a couple of sites in Pennsylvania that are doing the passive treatment with the iron oxide collection. So thank you for the presentation. It was excellent and extremely interesting.
Awesome. Well, thank you for contributing. Okay, at this point, our official program is over, but if anybody would like, I'm going to allow everyone to unmute and share their screen, or not to share screen, share their video. If anybody wants to do any further conversation.
Stefano, I
Yes.
had a quick question. This
Please,
is
you can ask that while I figure out how to do this for
Yeah.
all 100 people. So
I was thinking about graphite because, you know, it's used for pencils, obviously. Is it a pigment?
Mhm. Yes.
Mhm.
Okay. And if so, Dr. Mary, when did graphite like form in your giant mineral history?
Well, it's graphite is a form of carbon.
Right.
Yeah, it's a crystalline form of carbon that is midway between amorphous carbon and diamond. And so basically it depends upon the areas in the volcanic, I guess, activity, how much pressure is being exerted on the carbon, because if it's an enormous amount of pressure, of course, you get diamond, but intermediate pressures, you get graphite, which is more, it's really a two-dimensional lattice of carbon hexagons. And that's one of the reasons why it's used as a lubricant, because the layers of graphite slide over one another very easily. And that's a function of its structure, and it's also a function of its use as a pigment, because it's so easy to just use a graphite pencil. You know, there's no such thing as a lead pencil. A lead pencil is a graphite pencil, and that's the reason it slides so well. But it all depends on the reduction of carbon to its elemental form in the geological process, and then the pressures that are exerted on it when you have these upheavals and so forth in the surface of the earth. Does that make sense?
Awesome. Thank you.
So just a technical question or issue. I've been trying to promote people to panelists so they can share their video and unmute, but it seems like everyone's declining. So if you would like to ask a question, I don't know what's going on. I apologize. If you'd like to do so, if you'd like to participate, just go ahead and raise your hand, and then I can focus on each one of you and unmute you. I apologize. We've done this before, and I could make people panelists, but now that I promote people, I get these decline notes. Oh, okay. I see a hand raised. Awesome. Sandy Tizinski, I'm going to allow to talk. And Aiden Hendricks, I'm going to. Oh, you already are allowed. All right. Go ahead, Sandy, if you like, or Aiden. Oh, and then Julie, allowed to talk.
Looks like Aiden's having some mic issues.
Oh, okay. Sorry, I'm not looking at the chat.
Sandy says no questions.
Oh, okay. Sorry.
But I see Christopher, you are unmuted. Did you have a
Okay.
question?
I wasn't quite sure if I could actually be heard.
Yeah, you're good.
Can
Sorry.
you hear me okay?
Mhm.
Can you hear me okay?
Yes, go ahead.
Yes.
Okay. All it was that I know you guys locally drive various pigments for Hoover pigments as well, but regionally or geographically, and by sort of rule of thumb, where are most color pigments sourced, either in North America or worldwide? I know we were talking about azure and blue pigments being in the Afghanistan region of the world globally historically, but is there anywhere in particular that's well known for certain pigments?
Yes, I mean you actually have been trading pigments around the world for centuries. You know, for example, one of the other prominent natural pigments is called umber, and it's a piece of the best deposits are out of the island of Cyprus in the Mediterranean, and which is a piece of the ocean seafloor that's been picked up and, you know, has good deposits there. You get reds from all over the world, but you can identify by color the difference between a Spanish red, an Iranian red, a red that comes from the Great Lakes area of the US. So, you know, it actually depends on the actual shade you're talking about.
I see two Julies, Julie Beal and Julie Weatherington Rice. If you'd like to ask a question.
Yes, this is Dr. Julie Weatherington Rice. We actually use the coloration of the iron in deposits to determine the primary porosity of the lake clays of the glacial materials here in Ohio. And we find that when we're getting little to no matrix movement at all, and secondary porosity through everything, and Dan Keller knows all about my research on this, that the irons stay a blue-green color. We actually pulled some samples out from a very deeply buried lake down near Cincinnati that were more than 700,000 years old that were colored, quote, green rust, unquote. Dr. Jerry Bingham and I wrote a paper on it. And literally, as we opened the cores up, we watched them turn brown in front of our eyes. So they had stayed in that state for 700,000 plus years. Now, along the varves in between on the lake, they had gone to black because, of course, the oxygenated water had been moving through the varve layers through all that period of time. But the matrix itself had stayed in this incredible, unstable green rust. And I've never seen anything like it. It's the most gorgeous peacock blue I've ever seen. And it just disappears. And it's so frustrating because I'd love to be able to capture that color.
Just keep it away from oxygen.
Right. Well, you can't do much with it if you're going to bring it out and try to do something with it. But it maintains and it rips up and is found in newer glacial deposits where it's been washed over by pre-Illinoian outwash and put into the sands and gravels from pre-Illinoian ages, and you'll find these lake clay balls within the sands and gravels, and they're brown on the outside, and you go to open them up and they're peacock blue, and then they change in front of your eyes. But it's been extremely useful to use that coloration as a surrogate for doing determinabilities of primary porosities. And we found it to be very, very helpful.
Hey, Julie, it's Dan Kelleher. I'm so glad that you shared that, and thanks for being on here today.
Oh, for all my cracks and dirt, huh? I have a PhD in cracks and dirt. Okay. I have been mostly working with secondary permeabilities because it's so important in contaminant and in water transport. But the other thing that we find is that when we look at Illinoisan glacial materials and the colors of the reds and yellows in those soils, and then we look at them compared to the Wisconsin ones, and then we look at the Pennsylvanian aged sandstones that are iron oxide cemented and colored, that the intensity and the hues of the irons seem to become stronger and stronger and stronger with time and age. And I'm assuming that part of that is a time age function. Can you then create that same change with heat?
You can, with heat, you can make it go more purple.
Okay.
You can't go the other way.
So it's like, but it's like taking an amethyst and turning it into a citrine, which is done with heat, or it's not like that at all. It's not a restructuring of the crystal matrix of the mineral. It's
no, and again, amethyst and citrine are both quartzes.
Right.
So you're talking about the refraction of the impurities.
And that's the thing I think it's really hard for people to understand, is the difference between crystal structure and pigmentation. Mm-hmm. Because they really are very, very different, and they're doing very different things, which is why you can't grind up amethyst and get, a purple pigment.
Thank you for the comments. We need to close out.
Sure.
And thanks for everyone's contributions, both our participants with the questions and the chat, and our awesome panelists. And keep an eye out for further communications on LinkedIn and other social media from our organizing team for upcoming events. We're working on some really cool geology that aren't quite nailed down to the point where I can say what they are, but they're very exciting. And we also welcome emails for suggestions for future topics. So thank you again. Thank you, everybody. Thank you, our panelists. Thank you, the organizing team, and have a great weekend and a great Earth Day.
Thank you.
Take care.
Bye-bye.
Take care. Thank you.
Bye-bye.
Bye-bye.